I'd like to introduce Ram Huggahalli, who's a principal hardware engineer at Microsoft in the Azure Hardware Systems and Infrastructure Group. And Ram's focus areas are hyper-scalar systems architecture, SoC platform level interconnects, and accelerator architecture strategies for the next 2 to 4 years. And prior to Microsoft, Ram has been with the Intel Corporation, contributing to memory and I/O subsystem directions in various Xeon processors and platforms, large-scale HPC interconnect product roadmaps, and system-level simulation methodologies. And Ram holds MS degrees in electrical engineering and engineering management from Missouri University of Science and Technology. So Ram's talk is going to be titled Co-Packaged Optics in Future Server Designs. Ram, over to you. Thanks very much.
Okay, so I guess I can start sharing the slide.
Yeah, please do.
I appreciate the intro, Rob. Thank you very much. Very excited to be here and to be sharing some of the observations that we have at Microsoft. I've been working for Microsoft since 2019. The team that I'm part of is called the Azure Hardware Architecture team. And this is where we provide the architecture strategies and define them around the 2 to 4 year horizon approximately, right? So really a lot of the churn that happens in data centers, it's fun to see and fun to be able to observe the problems and engage with a crowd like this to understand how we can introduce new and cool technologies. So super exciting to be here. I've got 3 main slides and I want to take you through another familiar, I would say it's not a new notion, but another familiar notion of disaggregation. And on this slide, I want to mainly talk about where the need for flexibility and scalability is coming from, especially in the context of server designs. Co-packaged optics is not a new notion. I think we've had some excellent introductions to that topic again, and a refreshers from both Catherine at the beginning of the day, as well as Rob. So CPU itself is a new thing. The question is, to what extent is CPUs actually applicable inside a server box, a typical server? That's a topic that I want to focus on. You can have all kinds of applications of CPU, but what about server design? And it starts with making observations on where do we need flexibility and scalability. First, if you look at the data center application trends, it's just amazing in terms of the number and the range of external and internal applications that are running in data centers, right? It's ever increasing, it's already large, and continuously there's just so many things that run. And that variety, that whole range directly implies a proliferation of platform configurations and designs, right? It's the default inclination is essentially, I've got a new application, it requires a new combination of resources. Let's figure out how to take a baseline and configure it differently. If that doesn't work, let's just introduce a new design from the ground up, including boards and things like that. And that's sort of the default trend. And we are concerned, and some of the considerations to address the concern about that proliferation are to really figure out how to minimize the skews or the configuration. So if you minimize the skews, then we have uniformity in the resources, and we can effectively take advantage of that with our resource allocators and increase the efficiency of using those resources, increase resource utilization effectively. We also want to minimize platform design. They're so expensive to build, right? The development cost of every unique platform design is very significant. So this is something that I think really we want to have a handle on. The different types of I/O devices, which their own form factors. We have PCI cards of various form factors. You have drives of various form factors that all need to want to get in and sit in the same board, in the same 1U box. These are all, again, challenges. The fixed and rigid routing that we really need to sort of design to in PCBs is another challenge. And the default approach where you try to look at the worst case and you build an all-in-one design, that's looking to be untenable, right? There's significant mechanical and electrical design challenges as the range of applications increase. Trying to do all-in-one designs is just not cutting it. And you've got these new rack standards and chassis standards that actually encourage packing more things into the design, into a chassis. But that actually, to some extent, exacerbates the challenges. You can pack things in terms of volume, but how do you actually design the connectivity to all of the resources that you can actually pack into the system, right? So it's a non-trivial thing. That's something that we really are concerned about as well. And these platforms, it's important to note that they're quite different relative to the Ethernet switches, right? So if you look at some of the Ethernet switch designs and considerations of optics and optical integration, the nice uniform fan out is not the opportunity that we have here, right? We're looking at all kinds of front to back and back to front and crisscrossing of PCB traces, all kinds of messy scenarios, just to be able to design all these things into as fewer designs as possible, right? So those are some of the considerations that we have in mind. So all the discussions and the prior art and disaggregated systems and modular systems is starting to really make sense. And the question really is, how do we make it practical, right? So how do you actually really move in this space? And that's two pieces to it, right? There are two important pieces to it. One of them is, how do you make the physical disaggregation with flexible connectivity happen with the right interconnect technology, topology, all the componentry around interconnects? And what is the architecture that allows us to flexibly compose systems and pool resources, right? So those are the two top level challenges that we really need to be able to address, okay? The barriers, let's take a look at what are some of the hurdles, right? The concept is not new. The practical barriers include challenges that we still can't fit a lot of configurations within a U. So if we have to have another subset for which we need to make special designs, let's just do that. And it's an expensive thing to do, not always practical. And that large subset is a shrinking subset, right? So that's one counter to this issue. There's still a lot of aversion to introducing platform level cabling, right? Cost, size, operator error, cabling of any sort in a high volume platform is a thumbs down, significant aversion to it. PCIe, CXL, retimers, and switches, and again, in high volume platforms, they impact overall TCO, right? So if you introduce this in every platform and just scale to millions of platforms, it adds up very quickly. And the thing that I want to get into is, where does CPO come into this, right? The starting perception for our platform designers is that these appear to be a partial solution. I've got bigger problems. I'll get into some of the bigger problems in the platform, but we are solving the energy efficiency problem of certain interfaces, but I've got all kinds of interfaces in the platform. So it appears to be just a partial solution. So what is the opportunity for CPO then, right? It is a distinct step forward. So we have had other reviews and presentations. The characteristics look good. We have a certain set of targets in mind, and some of the numbers that we're hearing are very, very promising. So great promising technology relative to copper-based connectivity. But introducing any form of optical connectivity beyond copper cabling, it's going to meet even greater resistance. It requires further innovation. And it's particularly because these are volume compute platforms. Again, this is not Ethernet switch platforms. These are not specialized applications such as HPC or AI. These are volume platforms. So that's sort of the ultimate challenge. How do you get these technologies into volume platforms and make it all work? And it seems like we need to understand that CPO is just one component, right? It enables a lot of things, but we really need to envision an optical technology-based complete system that provides comprehensive benefits, right? And I'll essentially seed some thoughts here in terms of the kinds of things that need to go into an optical system, right? So I don't necessarily have a conceptual visualization. That is something that I hope, once we identify the key ingredient technologies, that we can work together to put together a conceptual system and work towards prototypes and eventually deployment. But some of the characteristics appear to be minimizing or eliminating the contention with other SoC chiplets. This is non-trivial. It's not like you can eliminate any footprint relative to CPO or equivalent technology. But the problem is that this package that our compute SoCs sit on, they're heavily contended packages. They're already large. Almost everything in the platform is wanting to get onto that package. So CPO, like chiplets, need to contend with other chiplets. The footprint is non-trivial, right? So that's something that we need to think about, and we need to obviously pay attention to the size of these chiplets, as well as consider things like 3D stacking technology, so that you can sort of hide these chiplets underneath other chiplets and other layers of a 3D stack. Another thing is we need to envision what full optical connectivity looks like all around our SoCs, right? So if the long pole and the dominant source of IOs in a CPU, in an SoC, is something like DDR, if you look at the pie chart at the bottom right, the gray piece and the orange piece is all related to DDR data signals and ground signals. So that's the dominant part that's burdening an SoC, and you're not directly addressing that with CPO, but you're focusing on, say, PCI and some other IO connectivity, you're not solving the problem, and there can be a perception that you're actually compounding what is already a bad problem with DDR. Right? We need to think about how do you actually enable dynamic composition of resources, and you need some kind of a switching technology, and you can't just throw in retimers and electrical switches everywhere. They potentially exacerbate the TCO problem. So you need to think in terms of high radix and small footprint optical switches with which you can have flexible, you can dial in flexible resource ratios and compose resources. And finally, fibers directly into that server compute SoC, that can be pretty intimidating, right? So we don't do anything like that at this point, obviously. It's all PCB electrical traces through a substrate and through a PCB. And so how do you get fibers into this? And can we avoid it in some way? Can we think in terms of optical sockets and waveguides through a board, and what are the challenges there? I'm sure that's been thought about, but anything to avoid a whole bunch of fibers coming out of an SoC will be incredibly important and useful to look at. I will stop there. I may be running out of time, Rob, but I'll pause there and take any questions. Or
great, thanks very much, Ram. That was really interesting. I'm just looking at the chat right here. I don't see any messages or any questions. Just for the attendees, I just reiterate, I mean, if you have any questions, either please feel free to enter them into the Q&A queue or into the chat, and we'll address those. And if you think of any other questions, we'll try to tackle those as we get to the panel discussion. Actually, Ram, though, maybe selfishly, I can ask you some questions. You outlined, and one of the themes I picked up from some of the topics that you mentioned was the need for composability and flexibility of your connectivity, and you think you can achieve that by using optics more widely in your infrastructure. The question is, by doing so, I mean, do you think there's any additional overhead in terms of performance hit that you might take by doing that? And is that tolerable, or do you really need to maintain the same level of performance but also enable this flexibility and composability? Is there any trade-offs that you can make there?
Yeah, absolutely. And I think it may be a longer discussion depending on the nature of the system. And but if you put forward things like memory technologies that you might be disaggregating, etc., even for those kinds of scenarios which stretch the requirements a bit, CPU is looking very promising. Some of the characteristics that we're looking at for in terms of picojoules per bit with short reach, die-to-die interconnects, and some of the latency characteristics, they look absolutely exciting. So if you look at the slides that I've got, I wouldn't make a big deal about needing even better latency and picojoules per bit. It's these other problems. The baseline direction of the technology is looking absolutely great. Let's just envision the fuller system around it.
Okay, great. Thanks very much.